Well, awesome. Thank you for having me. My name, and everyone can see the screen, correct? Before I go on?
Yes.
Yes.
Okay, awesome. Yeah, thank you for having me. My name is Christian Prem. I'm the product manager of biosolids equipment at Huber Technology. And actually, real quick before we go on, I just wanted to mention the course ID and course name are right here. If you haven't written those down already. It's a little, I think it was a little cut off from what the actual title of the presentation is, so just make sure you jot that down if you have not.
It's just a mute. I think we gotta go here.
All right. So as I was mentioning, I'm the product manager for mechanical biosolids equipment at Huber Technology. So that covers biosolids screening, thickening, and dewatering equipment. So I am not over thermal drying, but everything else is kind of in my domain. So I'm a member of the Water Environment Federation. I'm sure a lot of you are, Residuals and Biosolids Committee, and I'm on a member of the Solid Separation Subcommittee. So we're really tasked with analyzing upstream effects on solids handling processes. So that's kind of what I specialize in on that subcommittee and at Huber. So just breaking this down into four parts, and the last part just being questions. But part one, we're going to do a quick equipment overview. So we're going to go through what is sludge screening, what is sludge thickening, what is sludge dewatering. For a lot of us, this is just going to be a review, but it's also going to be kind of a baseline for explaining part two, which is the upstream process effects, which may affect performance of these three items right here, these three processes. So after that, we're going to go into part three, which is application on the plant scale. So distilling some of this information from part two down to a plant level. A lot of this from part two will be what I call descriptive, not prescriptive. So it's going to be describing things that we've analyzed on a kind of a meta scale, but might not apply to every individual plant. So we're going to kind of analyze that a little bit more in depth in part three. And finally, we'll wrap up with some questions and discussion. I welcome any questions or feedback that anyone may have. So looking forward to that at the end. All right. So jumping in on sludge screening. So what is sludge screening? It's the removal of inorganic materials and fibers from a solid stream, whether that stream be sludge, it could be FOG, food waste, or another stream. So to minimize the volume of screenings being hauled, there is integral compaction within the sludge stream. So our screenings and sludge are coming in, the sludge is exiting, the clean sludge, as we call it, is exiting here, and the trash, the debris, whatever have you, is being compacted in this zone right here. Typically in sludge screening, the removal of inorganics is being done under pressurized conditions, so we're not breaking line pressure. That is not true in every single application. There are some sludge screens that screen sludge via gravity, but primarily we're looking at a pressurized screen. So now that we've identified what it is, why do we do it? So reducing maintenance, so reduce digester cleanouts. We want to protect downstream process equipment. Protect downstream process equipment such as a dryer feeder, things like this, which are very expensive to replace or to clean out. Screening equipment out beforehand can reduce a lot of downtime. Safety, of course, protection of operations staff, reducing times that we're having to go into digesters or go into confined spaces to clean equipment out. Efficiency, higher biogas production, mainly at facilities with anaerobic digestion. Because we're removing the trash that would then make its way into an anaerobic digester, take up digester volume. Just less wasted space in your digester. And then finally, land application. So removal of any plastics or rags or material that might eventually make its way into dewatering equipment and then or drying equipment and then into sludge that we would land apply. And just ensuring a clean end product. So how does it work? Again, we kind of had that visual before, but our unscreened or dirty sludge, as we call it, is coming in under pressure. It's passing through this screw and then through a perforated plate and then out of this outlet, which we call the clean or the screened sludge. So all of the trash that is laden in that sludge, whether primary waste activated, is being caught on this perforated plate. So it acts passively. The screw is not turning all of the time, just when a differential pressure threshold is exceeded. So once that is exceeded, the screw auger begins turning, moving the screenings down the auger towards the compaction zone we talked about earlier with integral compaction. And then we have these two competing forces. We have the internal pressure of the sludge and the screenings, and we have the back pressure of a pneumatic retention cone. This does two things. We're maintaining the pressurized environment that we're screening under. We're also providing additional back pressure for removal of additional water in this compaction zone. So once we get to the end, the motor is talking with the pneumatic control panel over here. Once a certain torque threshold is exceeded, we're going to back the cone off slightly, let some of these screenings out, and keep it will actually turn the screw off and keep screening passively. So where does it go in the process? Usually it will go after primary or secondary clarification, not always the case, but primarily that's where you'll find it, and prior to a digester. That's where it's going to take out the most material and prevent the most costly of endeavors, such as cleaning out the digester. So the raw sludge would be pumped through the unit, through a flow meter and into the unit where we're measuring this differential pressure. The clean sludge or the screen sludge is coming out typically under 1 bar, 14 psi, and going into a digester. Now, if need be, we can pump through the unit and into a positive displacement pump. That would allow us to go up higher elevations if need be. So just a couple of other applications. So we've already seen the primary screening application or talked about that, but there's also preliminary screening. We've actually seen these installed on cruise ships in front of package MBR plants, waste activated sludge streams, digestate streams after a digester, pre-dewatering, side streams such as FOG receiving, food waste receiving for anaerobic digestion. So there's a lot of potential applications. But the primary or the premise of the machine is the same. It's solids liquid separation. We're taking out the trash. So we want to remove that so we can have a useful product at the end. So just a general sizing overview for sludge screens. There's typically multiple sizes across various manufacturers. Throughputs generally range from about 100 gallons a minute to 1,000 gallons a minute. Of course, that really depends on the type of sludge, whether it's primary, waste activated, digestate, etc. The solids concentration that we're feeding into the sludge screen, and some other factors. So inlet pressure, process flow pattern, several other parameters are also analyzed when sizing these machines. We really want to keep the inlet pressure to a minimum because, like we discussed, we have these competing forces over here at the pneumatic cone. And since that is under pressure, we want to avoid any potential for this screenings being pushed out of the machine. So we always want to keep this screened environment typically under, I'd say, 20 psi. Pneumatic retention based on the stream that will be screened. So we talked about the retention cone. If there is more grease, the sludge is greasier, we will see more extrusion under high pressures, meaning that in that compaction zone where the pressures are the highest, some of the sludge will actually start extruding through the perforations if our back pressure is too high. So in those instances, if we know that we're dealing with a sludge that has, FOG blended in or scum or something else that would make it more greasy, we will reduce the back pressure. If it is a primary sludge that's pretty well held together, we can increase the back pressure and increase the degree of dewatability of the screenings. Okay, so we tend to look at the strain press and for different facility problems or symptoms of problems. So if there are old headwork screens that may not be removing material properly, that can actually be a symptom. It can be a situation where we would see a lot of rags, a lot of material getting into downstream process equipment or downstream tanks. So that would be the sludge screen would be installed between the primary clarifier and the digester to remove those out in line. So a symptom would be frequent digester cleanout. So if you have a lot of trash in your digester, that can be a symptom that you're not removing a lot of that material at the headworks, and a sludge screen may be a good idea for your facility. We oftentimes consider these for facilities with primary clarifiers. Another one can be poor biogas production. If it has decreased from what rated values are, that might be indication that there's debris buildup, taking up useful volume for biogas production within the digester. And that could be another reason that we'd look at a strain press or a sludge screen. Another application could be on secondary clarification. So if you have material that's making its way through the bio process and into the secondary clarifier, you can protect your downstream thickening equipment or dewatering equipment by placing this screen in line. Another instance that we've seen is on the primary clarifier, but actually on the scum side. So when we're removing the scum from the clarifiers, a lot of times we'll see bottles, other floating trash making its way into the stream that can then make its way into the digester. We've actually seen where we've screened a scum layer through a sludge screen and then passed that on to the digester for biogas production. And then side stream. So again, we mentioned FOG receiving. A lot of plants are doing this, especially with anaerobic digestion as a high strength waste because of the high biogas production. But you can also introduce things such as coffee stirrers, forks, knives that might find its way into a grease trap. And so we want to remove those items with a sludge screen prior to going into a digester. Okay, so jumping on to sludge thickening. What is sludge thickening? It's, again, solids liquid separation. It's just a different kind of solids liquid separation. We're talking about biosolids and water instead of trash and sludge, liquid sludge. So in the thickening process, solids content is typically increasing while overall volume of the sludge is decreasing. Filtrate water is mostly free of solids and returned to the plant for treatment. We typically say around 95% capture of solids or higher is an acceptable level of capture for thickening equipment. So why do we thicken sludge? Reduction in size of downstream digesters and sludge holding tanks due to smaller volume of the sludge. So this means lower capital costs and overall footprint at the facility. Increased solids loading capacity of downstream equipment, such as dewatering equipment that might come post-digestion. We can recuperatively thicken solids in digestion to increase the bulk solids content. So all of those are areas where we might consider thickening. So how does it work? How it works really depends on the technology. Now, the premise is the same, but you have a lot of different types of thickening technologies, from gravity thickeners to gravity belt thickeners like this down here, rotary drum or rotary screw thickeners like down here. We have disc thickeners right here, centrifuges, thickening centrifuges, and DAF flotation. So all of those and others are ways to thicken. These are some of the most common. How does it work? So we'll focus in on one technology for this kind of application case study. So most of the principles can, however, be applied to other types. So the sequence would be a thin sludge stream is pumped from a solids holding tank. Typically, we say between 0.4 and 1% solids, but it can be plus or minus that as well. A flow meter is used in line, and that is used to calculate solids loading. So if you know your feed solids and you know your flow rate, you can calculate your solids loading. That helps us in the next stage, which is polymer injection and mixing. This allows us to inject a polymer that is going to flocculate the sludge. It's going to build us a nice strong flock that we can then drain the free water off of. And equally important to injection is mixing. So getting the mixing intensity correct is very important so that we incorporate the polymer completely into the sludge stream. If you undermix, it can require more polymer as you're not fully mixing that polymer stream into the sludge stream. If you overmix, you can really beat up the flock and actually require longer flocculation times in a reactor such as this right here to achieve proper flocculation before thickening. So on that note, flocculation reactor, we like to say this is not really mixing, it's just gentle agitation, and it's to promote flock development. So the mixing intensity is injected right here with some sort of checked valve or a static mixer, some sort of device, mechanical mixer. But really this right here is for retention time and for gentle agitation. So at the top right here, we've developed a flock and we're overflowing by gravity into the thickener. So the thickener itself, this is where the majority of the free water is separating out. Again, we thicken anywhere from about 4 to 7% or higher, depending on the process needs. Thickened sludge storage, this is usually an intermediate buffer tank of some sort that allows us to have process control between the thickener and the downstream tank. And then, of course, you have your downstream tank or digester that you're going to after thickening. So again, jumping into the flocculation tank, this is an example of what a flocculation tank would look like. You see a mixer motor, usually driven on a VFD to provide process control, allow you to speed up, slow down the mixer depending on what the sludge requires. It's really, really key to have good flocculation to make sure we can release the maximum amount of water. If you don't have good flocculation, you can have the nicest equipment out there, but it's not going to do anything for you. So it's typically accomplished in a flock reactor, like we mentioned, with the assistance of polymer. And the duration of flocculation time can really depend on the flow rate. How much are you sending to the flocculation reactor itself? Because that can influence retention time within a tank. The polymer type that you're using, the active polymer content, mixing energy implied, retention time, and other parameters. So this is at the top of a flocculation reactor. This is the sludge that's overflowing by gravity into the thickener. So the actual thickening machine, and in this instance, the disc thickener, it is we have the thin sludge coming over into the machine on the right over here. It is draining down a slope by gravity, and then the disc is carrying the sludge up the hill to the thickened sludge outlet that you see over here. So in this instance, one rotation of the disc is required to thicken the sludge and separate the filtrate. The free water typically returns by gravity. It goes, in this instance, through the mesh and to the head of the plant. The plows right here are really for turning that sludge over, releasing, or providing open area on the filtrate or the filtration surface that we see right here. So we're going from a lot of water trapped in the sludge flocks right here to that space being open for filtration on the backside. So that's what these plows are in there for. Also for centering or directing the sludge to the outlet. And again, we mentioned this before, it really is process customizable, but we see anywhere from 4 to 7% typically on thickeners. So the mesh itself, you can have on a belt thickener, you might have a belt with a mesh material. Similarly, we have a stainless steel mesh on a disc thickener that is backed by a perforated plate that you see here. Those in conjunction help to separate out the solids and the liquids. The type of media that we're using can really depend on the type of sludge that we're thickening, depending on the constituents, whether there's primary waste activated, if there's water treatment sludge with really fine particle sizes. All of those can impact the type of media that we use and the effectiveness of that media rather. For this instance, the disc thickener uses a 200 micron stainless steel mesh. It's a little bit difficult to see, but it's overlaid over top of this perforated plate. Okay, so now the last part of the thickening process, thickened sludge transport or storage and transport. So we're coming out of the machine right here. We're dropping down by gravity into the storage hopper. This storage hopper in particular is controlled with a pressure transducer. This allows us to send a 4 to 20 milliamp analog signal to our control panel, giving us process control. So if we want to let the level rise a little bit higher before pumping, we can do that. If we want it to pump almost continuously, we can do that based on an operator adjustable set point. But really, again, this provides a buffer tank between the thickener and downstream digester. This can be necessary if we can't drain directly by gravity into a digester or tank. Positive displacement pumps are typically required for these applications just due to the viscosity and back pressure that's exerted on the pump by the solids. We very commonly see a progressive cavity pump, rotary lobe pump, plunger pump, etc. So any kind of positive displacement pump is generally allowed. So lastly, just control of the overall system is typically supplied by the equipment manufacturer or by the system integrator. The type of oversight required usually depends on the technology selected and the method of operation. So really the control systems from manufacturer to manufacturer, from system to system, can really vary greatly, but it depends on what the goals of the facility are. So for an example, a disc thickener has lower throughputs than other technologies, but can run and has run 24/7 operations unattended. So gravity belt thickeners have much higher throughputs, but often require greater oversight and lower hours. So it's really a trade-off, and that has to be decided between each municipality, their engineer, and equipment manufacturers. Okay, so lastly, we're going to go over sludge dewatering before we get to part two. And this is really the exertion of mechanical or accelerated gravitational forces to remove free water from biosolids. Mechanical forces usually are in screw presses, belt filter presses. Gravitational forces are typically centrifuges, decanter centrifuges. We typically cannot remove bound water, as this is bound within the cells and must be removed through thermal forces. So we're still targeting that free water, even if it's tightly bound within that cell matrix. Okay. Why do we dewater? Again, volume reduction, similar to thickening. We're trying to reduce volume prior to on-site drying, off-site landfill, land application, other methods, maybe composting, any method of disposal or reuse of the biosolids. In general, and this is not always the case, but in general, we're going somewhere from 0.5% to 3%, up to 15 to anywhere up to 35%, really depending on the sludge stream. We'll get into some of the factors that can affect this number right here. I know that's a wide range, but it really is plant dependent, process dependent, and we'll look at that in greater detail in just a little bit. Additionally, reducing odor associated with higher water content. If we can reduce the amount of water that is bound up within the cells and within that sludge matrix, we can reduce the odor that we experience. So we're typically going from something like this, adding polymer, to something like this. This is actually showing a screw press pneumatic retention cone. So this is applying back pressure and helping to dewater in the last compression stage, which you see right here, the last compression stage of the screw press. And this would be our end product. So similar to thickening, it really depends on the type of technology in terms of how it works. Some of the most common types are belt filter presses. You see right here, we have a feed hopper, a gravity section, pressure section, and then a receiving container. Screw press right here. We'll go over that in a little bit more detail on the next slide. A decanter centrifuge, where you have the feed coming in, and separation is actually based on the relative density of the materials, the solid sludge and the clarified liquid. The liquid is going out this way, and we have a scroll that's bringing back the solids. And then sludge drying beds. A lot of time at smaller facilities or facilities where in hot climates where it might be advantageous to do so, we can pump sludge to a sludge drying bed, and it can offer a relatively cheap non-mechanical solution to dewatering. Okay, so again, like I said, for this example, we're really going to focus in on the screw press technology as a dewatering technology. You notice a lot of these sequences right here are similar to what we talked about for thickening. We have thin sludge pump that is feeding the liquid sludge to from the holding tank or digester to the screw press. We have a flow meter for measuring thin sludge flow, and similar to the thickener, we're measuring that flow rate. We have an assumed or a measured total solids. We use those to calculate a solids loading rate so that we can then dose our polymer. Then we have a flocculation reactor or piping for retention time, and we'll go over this a little bit more in detail, but we can have either a overflow floc reactor or a pressurized pipe reactor. We have our dewatering press where we're exerting mechanical pressure to increase the solids liquid separation, and finally cake transport. So just to aid in this, we're going to play a short little clip. Kind of walks through each of these processes. So over here, we have our sludge feed, our polymer prep. In this instance, this is a dry polymer system. A lot of times we'd also use something like an emulsion polymer system. So this is really where the sludge and the polymer get together, and we say they shake hands, get to know each other. This is polymer mixing. So in this instance, this is a mechanical mixer. We have the polymer coming in here. It's coming down the shaft of this mixer. We have the sludge coming through this way, and we have a turbulent mixing environment so that we're blending the sludge and the polymer in together. This can also look like a static mixer. It can be a weighted check valve. There's a lot of different options for this. We'll talk a little bit later, the pros and cons of some of the different types. So for this type of screw press, we have a pressurized floc reactor. You see the sludge coming in, and it's amorphous. It's kind of all over the place. It has not really formed into strong flocs. As it goes through retention time and through this piping, which is really just a wide spot in the line to provide additional retention time, you can see it starts to coagulate, flocculate, clump up until we get to the end where we have these much larger particles. Oh, sorry. Flowing through, and at this stage, we are entering the press. And this is the press where we have the liquid solid separation. This initial zone is typically for screening. We are draining off about 90 to 95% of the free water in this stage. It extends up to about this point. So the bulk of that water is going to be draining off at this point. After this, we enter our thickening stage, where we're going to be thickening that sludge up. We start gradually increasing the pressure by increasing the screw pitch, or the screw diameter rather. That's going to exert additional pressure on the sludge between the basket and the screw. So that's going to thicken the sludge up to anywhere from 7 to 8%. And then we really get into our high pressure zone at the end here. And this is where we're applying high mechanical pressure between the wedge wire basket in this case and the auger shaft. So at this point, we have a fully loaded auger. The pressure, the internal pressures are at its highest. And so we also have a pneumatic cone for applying back pressure to this zone so that the sludge isn't just shooting out of the end. But by having this back pressure, we're actually allowed to increase the dewatterability by 2, 3, even 4 percentage points. So just a couple of other key features I didn't touch on. The sludge is coming in over here after a flocculation. We're actually, since it is pressurized, we're measuring inlet pressure. The inlet pressure and the motor speed are directly proportional. So as we increase our inlet pressure, that's a good metric to say, hey, our screen zone's getting plugged up with solids. What we need to do is move those up the screw faster. So our screw speed will increase. It will help to move those solids along quicker. And then that pressure will start to die down, decrease, and our motor speed will decrease accordingly. At the end here, we have the dewatered cake that's going into our screw conveyor. There are a lot of different types of conveyance options. We'll go over those briefly in just a little bit. In this instance, it's a shafted screw conveyor. where we have a drive motor pushing the a shafted screw with the dewatered cake up to the end of the conveyor. Great. All right, so diving into some of the details now. This is the system washing. So we have a lot of liquid passing through this wedge wire basket. It can be wedge wire, it can be perforated plate. There's several different types of baskets you can have, but regardless, you're going to have a lot of solids, a lot of liquids passing through. So what we need to do is make sure that this surface stays clean so that we can maximize our filtration area. In this instance, we have separate washing of the inlet zone and the compaction zone. Like we said, 90 to 95% of our water is draining off in this initial screen zone. So that's going to be just naturally the zone that is gets the dirtiest. So to combat that, we have individual washing of this zone with solenoid valves that allow us to clean that zone independent of the compaction zone, which typically requires much less washing. Just a method to conserve water and not use as much plant water. So it's important to note that this is one of two steps for cleaning the basket. So this is the external cleaning of the basket. Now, while you may have these high pressure spray bars, cleaning the sieves, we really need another device for cleaning the inside of the basket. So for this, a wiper or a brush is used depending on the manufacturer. This is strongly recommended because even if we clean the outside of the basket, the inside can still get gummed up with material. So we want to have something that is making contact with the basket to clean that, but we don't want to use our screw as a sacrificial item. So instead, what we do is we have a wiper that runs along the flight of the screw, and it cleans off the inside of the screw, or of the basket rather, as it rotates. So not all manufacturers use this. However, solids can extrude through the basket if it's not utilized. If you have a gap between the screw flight and the basket itself, solids can actually get jammed between these and start pushing through the perforated plate or wedge wire, depending on the type of basket. So again, in this instance, the wear item is the wiper, not the basket or the screw. So that's really what we're after here. All right, and then control philosophy. So the main parameters that are defined are very similar to thickening. We have an assumed solids loading rate or an actual total solids measured from a TSS meter. That can be like a microwave solids meter or other type. We have thin sludge flow rate that we're measuring at our flow meter. So this is set at the HMI. We set a desired flow, and then we measure that flow with our thin sludge flow meter. The neat polymer dose in pounds neat per dry ton. The pounds active that are actually being dosed to the sludge can really vary depending on the type of polymer system and the active content of the polymer. The PLC is typically controlling the pacing signals for the polymer systems, saying it's an analog 4 to 20 milliamp signal, calling for the amount of sludge from or amount of polymer rather from the polymer pump, and also for the sludge feed pump. The systems can be fully automated and to allow for unattended operation. However, control over the sludge feed, the polymer feed, and cake conveyance is required. So just some examples of this automation could be using a press time clock, setting it to start at 4 a.m. and cut off at 5 a.m. We've seen that in some instances where longer durations are desired. Volume modes where you can tell the press to press 10,000 gallons per day. SCADA signals from issuing a call down to run. Also, we can have level signals that once we see a high level in an upstream holding tank, the press can begin running to lower that level to a low level cutoff point. Okay, so now we're out of the machine, we've discharged our cake, now we're at the conveyance side. There's a lot of different methods for this. Some of the most common are conveyors, pumps, and by gravity, and those can further be broken down into, for conveyors, we can have belt conveyors, shafted screw conveyors, shaftless screw conveyors, each with their own merits, and it really depends on where do we need to go and what's the easiest way to get there. Sometimes for For distribution conveyors, it can be easiest to have a screw conveyor with multiple outlets, such as this down here. So we have one outlet right here, another outlet over here. So this provides us with load leveling capability, or just the ability to drop sludge where we want it, when we want it. If we need to go around obstacles sometimes, or make 90-degree turns, a belt conveyor may be desired. Each, again, has its own merits. Sometimes belt conveyors can be a little bit messier because it's not an enclosed environment, but shafted screw conveyors can require multiple conveyors to make turns. Pumps similarly have their own pros and cons, usually operating under very high pressures, progressive cavity or hydraulic piston pumps. And then finally, and oftentimes the easiest, if possible, is just by gravity. We see some applications, if it's possible, where the sludge can just come out of the machine by gravity and into a dumpster or holding tank of some sort. So what's shown below is a shafted screw conveyor. Again, this is a shafted screw conveyor with multiple outlets. This is one that's taking dewatered sludge to a cake for hauling, or to a truck for hauling. Okay, and finally, screw conveyors. The drive motor is typically integrated into SCADA, or the screw press control panel, interlocked with operation of the screw press. We don't want the screw press running and the conveyor not running. Obviously, everyone can see why that would be a bad thing. So we always want our conveyor to be running and interlocked with that press, so that it is, we want it to cut on before the press cuts on, and sequenced such that anytime we're receiving sludge into that conveyor, we're running the conveyor and moving sludge along. Slide gates are optional. There's multiple types of slide gates that can be used. We can use electrically actuated. We can use pneumatically actuated. Pneumatically actuated, you typically need a compressor. Electrically actuated can be rather expensive, and you're suspending an electrical actuator up in the air. So it really depends on what the preference of the facility is. Support frames for these items are usually supported from the ground, or from suspension supports from the ceiling, or in this instance on this retaining wall that we see right here. Okay, and what about after dewatering? So we have several options for after dewatering. We have land application, composting, landfill, drying, etc. Just some examples here. We have landfilling, spreading of biosolids. Huber has a couple of options for drying in terms of thermal drying. We have a belt dryer, solar drying, a sludge turner, as we call it, or inside of a greenhouse, where we're using solar energy to dry the sludge. So lots of different options after dewatering. I would say that I am not the subject matter expert on that here at Huber. We have a team dedicated to thermal and solar drying. So if anybody has any interest on those items, I can provide contact info. Okay, so now we're going to jump into part two. So this is really where we take the knowledge that we have from part one of these processes, and we look at what can affect all of those processes.
Hey,
and
Christian,
as you
can you hear me?
I'm sorry?
Can you hear me? It's Hunter.
I can.
Hey, we're going to take a 2-minute break real quick, and I figured we'd also see if anybody had any questions. I know that was quite a bit of information we covered fairly quickly, so just going to ask the crowd if they have any questions, comments, anything. If not, we'll get back into it. I think we're good here, Christian. Sorry to cut you off.
No problem. Okay, so as mentioned, we have quite a few things that can affect the dewatering, the thickening, the screening. These are just some examples. We're going to look at preliminary treatment, primary treatment, secondary treatment, stabilization, solid storage, tertiary, side stream, polymer prep, and flocculation. So it kind of feels like this is the whole plant, and it really is. So we want to understand these solids processes from a holistic plant perspective, because in reality, each of these items can affect performance in their own way. So starting out at preliminary treatment, we have the type of headwork screen. So bar screen, step screen, perforated plate screen. So all of these are different types and can remove different amounts of material. Perforated plate screens, we're usually removing much finer material, much more material. That's not always the case, but in general, that's what we're looking at with a perforated plate screen. What we're seeing with perforated plate screens is that there's a higher degree of fiber capture than with bar or step screens. This can actually remove binding material that will make its way into the primary or secondary clarifiers and into the sludge that actually holds that sludge together. So while it can be great to remove at the headwork stage, it's also worth noting that by changing from a bar screen to a perforated plate screen, you may be decreasing your sludge dewaterability. So from a solid screening perspective, if we have heavier screenings load, that is leaving the headworks, because of poor screening, we might see that ending up in the solid screen, which is an acceptable place for it to be, versus a digester downstream tank. But for thickening, we have the possibility for ragging if we have poor headworks capture. If rags are bypassing, these can get caught in trunnion wheels and different parts of thickeners that can impede performance. And dewatering, so in general, higher headworks capture equals lower cake solids and higher polymer consumption. Again, this really goes back to that binder material that we talk about, the fibers that make their way into the sludge. So as we're removing more and more quantities of those fibers and binding material, our dewaterability is going to decrease. A couple of images here from Bavaria in Germany that we have. So this is before and after a headworks upgrade and installation of a solid screen. You can see all this material over here in the dewatered cake before the upgrade, and then the minimal amount of material that's in here after. So while this is obviously preferred because it gives you a much cleaner end product, it actually decreased the cake solids dryness by almost 1%. So that is something, no other process changes being done was seen to have an effect on sludge dewatering. So continuing with preliminary treatment, the type of grit removal that you have. So vortex, fine grit, lamella separators, aerated grit tanks. There's a lot of options rather out there. So the removal level oftentimes depends on the type of technology that you're using. We can have 95% greater than 200, 175 micron nowadays. So typically less grit means lower wear on downstream pumps and equipment, which can be helpful when you have solids, progressive cavity or rotary low pumps feeding solids to thickening and dewatering equipment. It can also cause a lower dewaterability because the more grit that you have, that is more inert material that does not require polymer and actually acts as a binder of sorts, similar to the fibers in primary. Primary sludge is typically associated with higher cake solids. So why is that? If you look over here on the sludge, this dewatered sludge, you can actually see the fibers sticking out of this sludge. So this is a fibrous sludge from a blended stream of waste activated primary up in Maine. So as you can see, this is pretty high cake solids, and this is due to the binded or the binder material that is within this primary or blended stream. So it assists in flock formation. It usually reduces the time required to achieve an acceptable flock, and leads to higher cake and lower polymer dose. In general, we see that a higher ratio of primary to secondary solids will lead to higher cake solids. That is not always the case. It can really depend on downstream digestion processes, but in general, higher primary leads to higher cake. So cake solids of 20 to 30% are possible depending on the process and blend ratio. Another factor that we see is the nitrogen content in primary sludge versus waste activated. If we have just a waste activated sludge stream, the nitrogen content can be upwards of 8% versus around 3% for primary sludge. Nitrogen is very similar and sort of as a surrogate for protein within the cells, and has been linked to lower cake solids. So if you have a heavy industrial contributor that is contributing dairy, for example, with high protein content, that will usually lead to lower solids dewatterability. And primary sludge does not have those higher degrees typically. So you're seeing higher performance on those sludges. Extra polymeric substances, or EPS, is typically found in waste-activated sludges in much higher quantities than in primary sludges, also found in digested sludges, and this is really in every sludge matrix, but to what degree it is in the sludge matrix depends on the process. And water can actually adhere to this EPS and can be bound within this EPS. And it acts as sort of a gel, or almost like a Jello. And if you've ever squeezed Jello, you know that you can't get the water out of Jello even though it's in there. So this is kind of our example of a cell and our EPS bound to that cell. So we have our loosely bound EPS, that's this filamentous looking material right here, and our tightly bound EPS right here. That is protecting some of the internal bound water that we were talking about, and also all this water in the interstitial spaces. So the more EPS that we have, the more of that water is bound up in this matrix and not available for easy drainage. So depending on how we treat that, there are methods for reducing the amount of EPS, allowing for cell lysis and dissolution of the loosely bound EPS, which can lead to higher water removal. But in general, your waste-activated sludge streams are going to have more of this. Your primary streams are going to have less. Okay, so staying with primary treatment, but now moving to the top of the clarifier, we'll talk about clarifier scum. So if we are batch feeding clarifier scum into a tank where it goes to dewatering, this can cause a weaker flock or higher polymer dose if not stabilized prior to dewatering in some sort of digester. If it's screened, it can be sent to a digester for increased biogas production. If it is not, it can lead to higher polymer doses and lower cake solids, because again, we're introducing a greasy material that makes it harder to flock that material. Sludge screening should be considered for primary sludge streams. We talked about that earlier, so I'm not going to spend too much time going over that again. It's important that we do this at facilities considering THP, or thermal hydrolysis. This is a very expensive process, is not widely seen, but if this is seen at a larger facility, we would want to consider sludge screening upstream to protect that expensive downstream equipment. Okay, so moving on to secondary treatment and the effects that this can have on performance. So can my bioprocess influence downstream thickening and dewatering performance? And the answer is most certainly yes. One of the largest that we've seen in recent years is biological phosphorus removal. Phosphorus can be released if sludge is sent to an anaerobic environment after biological treatment. And while that BioP removal is very important to meet nutrient removal requirements, it can have negative effects on dewatering. And again, this is, descriptive, not prescriptive. So, just because we're saying it's bad for dewatering doesn't mean it's bad for the plant as a whole. It's just something to be aware of when making process changes. So in those anaerobic environments, the phosphorus will actually bind with cations such as magnesium. That is a divalent cation. These divalent cations, that can be bad because these divalent or multivalent cations help to reduce the water bound inside of the flock by actually bridging the space between the negatively charged flocks. So a lot of chemistry, and I'm not a chemist myself, but the simple version is with divalent cations, we're actually linking all of these bacteria flocks and their extra cellular biopolymer strands, which in turn will reduce the amount of space between available for water to fill up between those cells. So in turn, that will release more water into the bulk water, the free bulk water fraction, allowing higher dewatterability. So very sciencey and sometimes a little bit over my head, but Dr. Matt Higgins of Bucknell University has studied this phenomenon alongside Dr. John Novak from Virginia Tech. So this is something that we look at when we're talking about BioP removal at a facility. Myself and my engineers would look at what are the potential impacts of the BioP removal, the precipitation of the phosphorus, and how that could impact the chemistry downstream. So this is another example of that. We have our divalent cations right here. Those are binding these two cells. You can see there's a smaller amount of space for water to exist. But with monovalent cations, since our divalent are taken up, there's all of this interstitial water. So this interstitial water likes to hide between these cells, and if it's hidden here, it's not in the bulk water fraction, so we can't really dewater it, and it would need to be done thermally, which, as everyone knows, is much more expensive. So BioP continued, if not handled properly, struvite precipitation after BioP can lead to scaling inside of machines, can lead to premature corrosion. There's a lot of negative side effects of struvite precipitation in downstream equipment. You can get reduction in your flowable area within pipes or fittings. Obviously has its own effects of reducing throughput area, increased back pressure on your pumps, et cetera. So since struvite contains magnesium, formation can reduce soluble divalent cation concentration, which decreases dewatterability. So this really goes hand in hand with what we were discussing previously. So how about chemical P removal? So with alum ferric-based coagulants, this has been observed by many to improve sludge dewatterability for primary streams and mixed sludges, but reduce dewatterability for waste activated only streams. So it's really kind of a mixed bag. If there is primary in the sludge, you can have blended into the sludge, your performance can increase. If it's a straight waste activated stream, your performance can actually decrease significantly, similar to BioP removal. The actual mechanism for this action is still under investigation, but the takeaway is if primary is involved, there's a good chance for dewatterability to improve. If it is not involved, there's a good chance for dewatterability to decrease. And just a reference case study, if anybody's interested later on a good paper for this. So jumping over to a different type of process, the MBR, it's a great process, can be a great process, but it utilizes fine screening at the headworks. So this is an instance where we have to take a holistic plant perspective and say, okay, our headwork screens are making sure material doesn't get into our MBR, but because of that, we're also, those fibers that would be found in the sludge are now being removed, or a great fraction of them are being removed. So we typically see low fibrous material in the sludge. These tend to be more difficult to dewater than as compared to conventional activated sludges. So you can see a decrease of anywhere from 1 to 5 percentage points of cake solids, depending on the degree of screening upstream. And then finally, just wrapping up secondary treatment, other items that can affect performance. Like we said, EPS holds flocks together, but it can also trap water within flocks. So it's kind of a necessary evil, but mitigating large amounts of that can increase dewatterability. And then excess biocolloidal material typically occurs either in the biological stage or in the anaerobic digestion stage, and that can lead to higher polymer dose required to bind solids together. So we'll get to digestion in just a little bit and the effects that has, but in general, if we have anaerobic digestion, our polymer dose will increase significantly. Okay, so talking about stabilization. So thermal hydrolysis. So we talked about this briefly before, but in a nutshell, it's a sludge pressure cooker. So we have a pulper, a reactor, flash tank, and anaerobic digestion, which then goes to post-dewatering. Through this process, we have a significant reduction of volatile solids and a reduction in viscosity of the material. Excuse me. This allows for increased loading rates to digesters. So, and what this also does for cake solids is it increases the throughput, the cake solids, and the capture rate significantly, while typically reducing the polymer dose as compared to non-THP treated solids. So it can improve cake solids by anywhere to 20 to 50% of non-THP levels. The primary and secondary ratio within the process can really determine the overall level of improvement. So just as an example, all of our installations on THP solids are achieving greater than 30%. And this is shared by most technologies, whether that be belt filter press, centrifuge, other screw presses, et cetera. So very capable of increasing the solids. So that is one added benefit of THP. So moving on with digestion, we're really looking at stabilizing the solids while reducing pathogens and volatile organic content. Lower VSS will generally correspond to increased dewatterability. That's not always the case. If we have a lot of inorganics from industrial contributors or water treatment, that can actually impair dewatterability. So it needs the type of volatile solids reduction needs to be evaluated on a case-by-case basis. Aerobic versus anaerobic digestion can also impact performance. So aerobic can lower VSS. However, based on Hubert data, we've seen that it's not usually as much as anaerobic, although that really is case-by-case basis. So it depends on the amount of aeration. It's really plant-specific. But anaerobic can reduce volatile solids significantly depending on the solids retention time. However, it can also increase the colloidal material that we were talking about, which is essentially just little pieces of the flock that are breaking off into suspension and can increase the monovalent to divalent cation ratio that we talked about before. So those are both the negative effects on dewatterability, and the volatile solids reduction is a benefit. So really it depends, the balance of those things depends on the performance that we'll see. So it can vary between significantly decreased dewatterability if we have a rather short SRT to significantly increase dewatterability. So again, has to be evaluated on a case-by-case basis. Usually depends on if BNR with BioP is present. As mentioned previously, if BNR with BioP is used in conjunction with anaerobic digestion, that can lead to significantly impaired dewatterability. And dewatterability. Again, depends on what we're sending to the digester. So with digestion, we're usually getting higher solids concentration to dewatering versus that coming straight off of a secondary clarifier. Higher feed solids concentration usually leads to increased solids loading rate. So if a piece of dewatering equipment can do 400 pounds per hour at 1% solids, it might be able to do 550 pounds per hour at 2% solids. And that's pretty equal across the board, across the type of technology. So if we're able to increase the feed solids concentration, we can also increase the throughput that we're able to get through dewatering equipment, which can lead to a downsize in equipment at initial design and reduced overall cost. Recuperative thickening is a type of thickening that we talked about previously that can increase the feed solids within a digester without thickening the whole stream. So instead of going before digestion, we have it as a side stream where we maybe pull out at 1.5%, thicken up to 5 or 6%, and put it back into the digester to slowly increase the thickened solids the solids concentration over time. And this is just an example of that where we have a thickener right here. It's recirculating flow to the digesters, thickening up the solids content within that digester to a desired amount. Wrapping up stabilization, digestion, as we've said, can break down organic waste, release water from bound to a free state. So we're taking that the water that's bound up in those cells, we're able to lyse those cells, release that free water, which increases the degree of dewatterability. Because again, we're after that free water in the cell matrix. So if we're able to have more of that, we're going to increase the amount of dewatterability that we can expect. Finally, different types of digestion, thermophilic, mesophilic, T-pad digestion. There's obvious differences in the biogas yield. There's also differences in dewatering performance. So thermophilic is thought to generate significantly more EPS as compared to mesophilic temperatures. So if you remember EPS, the more of it that there is, the more gel-like the cells are, meaning the more difficult it can be to squeeze water out of those cells, or out of that matrix. This leads to poor dewatterability characteristics. Mesophilic tends to have lower pathogen destruction gas yield, but higher dewatterability. In the end, volatile solids reduction can offset adverse effects from thermophilic digestion, but it really depends on the SRT and the amount of volatile solids that we're destroying. Okay, Hunter, do we want to take a break and ask any questions now, or do we want to just keep moving on through?
You guys need 5 minutes? You guys want to keep going?
Take 5.
I'll take that to just keep moving. So thickening and dewatering. So we're going to move now to solid storage. Thickening and dewatering rely heavily on a consistent feed solids concentration. Mixing is key to maintaining a homogenized and consistent concentration going to the process. So just as an example, if we assume 1% solids is going to our dewatering press, and we enter that into the HMI as one of our assumed parameters, but the actual feed solids is 1.5%, our solids throughput is 50% greater than what the PLC is seeing, which means that our actual polymer being delivered is 50% below what is actually needed to achieve acceptable performance. So a well-mixed and optimized upstream process can help to minimize these discrepancies, which can waste polymer, can lead to lower dewatterability in terms of cake solids, can lower your capture rate. So having large fluctuations upstream can really impair dewatering equipment from functioning as it should, and thickening equipment for that matter. So this can sometimes be circumvented if we have inline total solids measurement. This needs to be evaluated on a case-by-case basis, as total solids measurement, inline solids measurement is typically very expensive. But if it is incorporated, we're taking the actual measured instantaneous total solids value, and we're inserting that into the PLC and into the HMI instead of an assumed value. So this can help us to be a lot more pinpoint in our estimations on polymer dose and feed, polymer dose and feed solids. And a corresponding pacing signal would be sent to the polymer pump based on real-time values, which we would not get from an assumed value being entered in. So tertiary filtration and tertiary processes. So a lot of times we'll see disc filters such as this one down here at the end of a plant to either bind up and remove polish, phosphorus, remove TSS, other materials. However, the fine solids cause a greater relative surface area and more surface tension within a dewatering press. So whether that's a press, a centrifuge, a belt press, a lot of times the smaller particles can bypass the dewatering equipment. The alum can also change the solids characteristics and cause higher poly doses and lower cake solids. So it's just it's worth noting that if considering tertiary filtration with disc filters, that it may impact the dewatterability of or thickening depending on where the solids are going from the disc filter. What we have seen is that it typically requires significantly lower throughputs if we're sending large amounts of very small inorganic solids to correctly flocculate and then dewater those solids versus just biological sludge. So side stream processes, co-digestion, it's been a pretty hot topic over the last decade and longer, but the idea is that we're increasing biogas production in an anaerobic digester through addition of high strength waste. So whether that be FOGs or fats, oils, greases, whether it's food waste, other organics, we're taking those, inserting them into the anaerobic digester so that they can boost our biogas production. This also has an effect on dewatterability, and it really can vary vary strongly depending on the feedstock. So if considering food waste or FOG acceptance, it's important to note what kind of waste is coming into the digester so that we can identify the effects that that will have on the downstream processes. So we mentioned this previously, but streams with higher protein contents usually can decrease dewatterability. It goes back to some of that nitrogen content within the matrix that we were talking about. Higher polymer dose, lower cake solids are oftentimes seen, and lower throughputs are also seen with, excuse me, streams with a high dairy or high protein content. Some studies have found that by adding certain types of food waste up to 60% by mass in your digester can actually improve dewatterability. There's an inflection point after 60% where they've actually seen cake solids and other dewatterability parameters decrease, but up to about 60%, there in some instances, they found that to be beneficial to dewatering. We talked about this in the sludge screening section, but sludge screening can separate the unwanted debris and material from the high strength waste prior to going into a digester so that you have a clean fuel source for biogas production. So just some physical and chemical impacts on dewatering. pH, typically, if it's very low, can impact our polymer dose, drive that up. Total dissolved solids, if it's very high, can increase our polymer dose. That is because if we have a high TDS to TSS ratio, there's a lot of charge sites that are being taken up by the polymer on those dissolved solids, and they're not able to interact exclusively with the suspended solids. So if our TDS is lower, we typically will have a lower polymer dose. Higher, we will have a higher polymer dose. And these are all parameters that we would evaluate in a laboratory setting. If we were sent a laboratory sample of the sludge, we would analyze each of these parameters. Volatile suspended solids, this is pretty well known, but if they're high, we tend to see a lower cake solids. If they're low, we tend to see a higher cake solids. Chloride content can lead to higher polymer dose. And potential for premature corrosion if levels are too high. That can really apply to any type of equipment if our chloride values are greater than, say, 200 to 300 milligrams per liter. So polymer preparation and dosing. Polymer flocculant is typically used to bind solids together in flocks, which assists in thickening and dewatering. Most sludges carry a net negative charge, which means that we use a positively charged or cationic polymer. That is, I'd say, the most common, but not the only solution. So, some sludges, depending on the process, may require anionic. We may need to dose additional coagulants, pH stabilizers, or other solutions. Identifying optimal polymer via bench testing is able to reduce polymer demand significantly. So just an example that we have right here, these are 3 cationic polymers, all of which are being dosed into a sludge with very unfavorable dewatterability characteristics. A special type of digestion, which really impairs the sludge from flocking easily. So in this instance down here, we have a polymer dose of 61 to 62 pounds active per dry ton for this polymer. If we go up here to a similar cationic polymer, but with a higher structure and higher molecular weight, we're actually able to significantly reduce that polymer demand. And, it's still a cationic polymer, still very similar in composition, but just by making subtle changes in the molecular weight and structure, we're able to reduce the polymer consumption by almost 20 pounds per dry ton. So it's not always the case, of course. The very next sludge sample that comes in, these might be flip-flopped. So it really should be evaluated on a case-by-case basis, especially if process changes can occur or do occur. A bench test of some sort should be performed to ensure that the polymer that the site is using is still applicable with the updated process flow. So most manufacturers will have a laboratory of some kind at their facility. This is an example of our laboratory at our facility here in North Carolina. The principal tests are, as mentioned before, total solids, volatile solids, TDS, TSS. and polymer dosage. Polymer dosage is sort of secondary to these other four because really we're more after polymer determination, which is the primary objective up here. Some other chemical tests that are performed are shown right here, and each of these parameters can also affect the amount or type of polymer that we choose. So these are all evaluated for every sample that we would test. So polymer prep dosing continued. Underdosing polymer, pretty well understood that underdosing polymer you have low capture rate, low cake solids, lower throughputs because you have lots of free water still bound in the sludge matrix. And it's not able to escape as freely as if you have a better polymer dose. I did say better, I didn't necessarily say higher. We'll talk about that in just a moment. But in this instance, we have a lot more free water that's separated off of the sludge as compared to this sample over here. So overdosing polymer, just like underdosing polymer, can have equally negative effects. It can waste money. So if you're overdosing polymer and don't need to, it can waste thousands of dollars a year. Cake hauling and polymer are oftentimes some of the largest cost consumers in a wastewater plant. So reducing the amount of polymer that we're dosing can significantly reduce the cost that we're expending. A lot of times this can be seen by a kind of a milky white appearance to the filtrate. So even if our capture rate is very high, excess polymer that is not binding to the sludge can blend in with the filtrate stream and would appear sort of milky white instead of clear filtrate. So unbound excess polymer can bind belts, it can bind mesh, other filtration surfaces. So we really want to use as little as possible while maintaining acceptable performance. And it can actually impede thickening performance, in particular if flocks are created that are too large and do not allow for free water filtration. So a great video, and unfortunately I was not able to get permission at the time of this presentation, but this is a great video to see the effects of overdosing polymer. This operator actually has a Huber S-disc thickener and goes through overdosing versus correctly dosing polymer and the effects that can have on performance. So if the flocks are too large, we actually have free water that is still bound up in those in that matrix that can't escape. Even if our flock looks great, we might not be able to drain that off. So if we actually reduce the polymer a little bit, make those flocks a little bit smaller, we can then turn that sludge over and release more free water. Okay, continuing on with this, the type of polymer system, dry versus emulsion, the type of polymer itself, linear, branched, or cross-linked. These are all things that we would evaluate in our lab, and really any manufacturer should evaluate in their lab when sizing equipment or preparing a bench test. Identifying the proper type of polymer is really key to identifying a way to get those solids to flock correctly. Just some other things, measurement of solids concentration, we mentioned this previously, has a high upfront cost, but can also save significantly on polymer. So if there is an estimated fluctuation of, say greater than 0.7 to 0.8% feed solids per hour to dewatering, it might be recommended to include something like this in the overall design. But that really depends on a cost-benefit analysis by the individual facility. If something like this is considered, it's oftentimes a good idea to consider automated dilution water control. So we dilute polymers typically between 0.1% and 0.25% in solution. And it's important that once we find the optimal solution that we stay there. So we're not fluctuating, up to 0.4% or down to 0.05%. We really want to stay locked into that area where we are. So automated dilution water control, if we have inline TS measurement, can help improve process performance. So now that we've activated our polymer, we're at the injection point into the sludge line. We want to talk about mixing energy. So this can look very different depending on the application. We can have something like a mechanical mixer here, where we have a VFD-driven impeller, VFD-driven motor driving an impeller that can blend the sludge and polymer at variable speeds. We can have a check valve, a weighted check valve that allows us to increase or decrease the weight that we're applying to the valve seat. But really, it's evaluated on a case-by-case basis. But at its core, this is designed to impart turbulences into the stream to blend the polymer and the sludge together well. We want to really completely incorporate those two components. This must also be optimized and is an important part of the process. Plants with thicker sludges, we see greater than 2.5% may want to consider variable speed mechanical mixing, and I'll go into those reasons in a minute. But it really, again, depends on the specific application. So mechanical mixing can reduce polymer demand by as much as 40%, depending on the application, versus static mixing. It can improve dewatered cake solids as much as 2 to 3%, but it really should be piloted to determine the efficacy. We also would have a reduced head loss with a mechanical mixer versus a sometimes up to 30 to 40 psi loss across a check valve. So that means less wear on your pumps feeding dewatering or thickening equipment. So the primary driver for considering this for higher feed solids applications is reduction in dilution water by up to 50%. So using a mechanical mixer actually allows us to go up to 0.3 to 0.4% neat polymer in solution versus a much lower 0.1 to 0.25 with traditional static and check valve mixing. So it can reduce the hydraulic loading rate to the thickening and dewatering equipment by reducing the amount of dilution water we're injecting. So just as an example, the polymer solution rate, so the dilution water, the carrier water plus the polymer can sometimes exceed 15 to 20% of the total sludge flow. So so by reducing this by up to half, we can significantly improve performance because we're injecting less water that we then have to redrain in the dewatering stage. Mixing energy that's too low may require higher polymer doses because we're not fully incorporating that polymer into the sludge matrix. Mixing energy that is too high can destroy the flock. So we really have to tune that and find the delicate balance in there. Variable weight check valves or VFD-driven mechanical mixers oftentimes provide some of the most adjustable solutions because on the VFD, you can turn up, turn down the speed. With the weighted check valve, you can add or remove weights, move them around on the lever to get the mixing intensity that you want. Okay, so moving on to one of the final stages before the actual thickener or dewatering press. We have flocculation time. So a very important stage, as we mentioned in the thickener and dewatering sections earlier. So we're providing reaction time for the polymer and the sludge to interact, promote flocculation in a low turbulence environment. That's key. That low turbulence is key to developing a strong flock prior to going into these mechanical machines. This is post-polymer injection and mixing. So generally, for a flocculation tank design, we would be injecting the polymer and mixing it right around this point over here, right before the flock tank. On a pressurized design, we would be injecting it up here, and then this pipe length right here would provide the retention time. Each has its benefits. This can sometimes require a greater footprint unless it's run along the machine like this, but it also means that you don't have an additional motor to maintain and a tank to clean out. So each has its pros and cons. So too little flocculation time can lead to lower capture and lower cake solids, anywhere from 1 to 5% cake solids or lower. And this is really evaluated on a case-by-case basis, the amount of flocculation time. Primary sludges tend to require less, or primary sludges or sludges with primary content tend to require a lower amount of flocculation time versus straight waste activated or digested sludges. Too much flocculation time generally not seen as an issue from the Huber experience and perspective. So now we're going to move on to part 3. So this really just consists of 4 bullet points. So who cares? What can I do about it? Differences in sludge types from Huber lab and pilot experience, and then pilot testing. So that will be rounding us out 2 questions. So why is it important to understand the potential performance impacts? These performance impacts, depending on their severity, can cause higher hauling costs if dewatterability decreases. We can have higher polymer costs depending on the application upstream change. This could affect thickening and dewatering polymer dose. So, for example, if we're thinking about moving to anaerobic digestion, we should think of the additional effects that might have on the downstream dewatering and thickening. There's always the potential for higher wear on components, higher O&M costs, sludge screening, thickening, or dewatering. And this is really, I should say, based around if we're considering receiving side stream, such as materials such as fog, we can start introducing lots of screenings into the facility that are bypassing the headwork screens. So considering sludge screening, that application may be desirable. That those materials can also make their way into thickening and dewatering processes. So what can I do about it? So weighing the pros and cons of upstream changes on downstream processes. A lot of times what we're doing upstream is very important, whether that be digestion type, bio-P removal, meeting effluent requirements. But we just need to realize that a lot of times this will have downstream effects. So should be aware of the potential impacts that these process changes have on screening, thickening, and dewatering. Make sure that piloting of technology is done after known or expected changes, if at all possible. If it is not possible, we need to ensure that the engineering team, the system manufacturer account for upstream process changes in their equipment sizing and performance estimates. So a waste activated sludge is not a waste activated sludge, if from facility to facility. The manufacturer and the engineering team should make sure that they analyze the process, the entire process from a holistic perspective to make sure that the performance estimates that they are providing are accurate to that sludge type. So again, evaluating potential solutions with the understanding that not all sludges are the same. So going on to these few slides, just wanted to point out that this is some data from our lab and from our pilot program. As we can see, these are all primary sludges, but the feed solids, the total dissolved solids, the VSS, the pH, chlorides, phosphates, and ammonia can all vary significantly from sludge to sludge. So this is to say, you can't expect, 15% or 20% at every facility. It really needs to depend on the specifics of that stream and of the upstream processes. So this is waste activated sludges. We have some mixed sludges here going all the way from 0.5% up to 4%. TDS going anywhere from 600 very low to 2600 very high. Talked about earlier, this can impact polymer dose. VSS from 57 all the way to 93, that can impact cake solids. pH, which can impact material selection and polymer dose. So a lot of differences here that should be evaluated significantly. We like to see a lot of these characteristics be incorporated into specifications when we're designing a plant, so that it's understood by all, including the engineering team, that these factors do in fact play a part into performance and have been accounted for. Okay, so with pilot testing, so the primary objective here is to optimize performance on the existing sludge. So slightly different from a bench test, we are analyzing full-scale performance at this point, whether that be throughput, cake solids, polymer consumption, or all of the above. Some of the additional benefits for operations or city staff could be getting familiar with the equipment prior to purchase, understanding actual performance values, and comparing technology side by side. Most manufacturers do have pilot equipment of some variation, whether that be for screening equipment, thickening, or dewatering. And it's highly advisable to consider piloting if possible to determine actual values versus those obtained in a lab setting. So these are just some of the tests that we would perform in a screw press pilot. This right here is a containerized screw press pilot. It's kind of an entire system within a container. So this would be delivered to a site. We would run our testing. We would write a report and deliver that to the staff so they can see what type of performance they could expect with a full scale machine. And again, this is thickening equipment. So what we saw previously was dewatering. This is thickening, again, in a trailer or a container. Allows for confirmation of performance prior to equipment purchase. So it's really important to identify any process changes which could alter system performance between pilot and full-scale installation. So honest and open discussions between the city, with the engineer, with the manufacturer should be had to assess the impact that any potential changes could have between pilot stage and full stage install. So this should play a video. Just we talked about the disc thickener earlier, and this shows this in operation where the free water is draining off, the sludge is thickening up, and then going out of the outlet on this side. So through a pilot, we'd be able to optimize this system, run higher, lower throughputs, higher, lower polymer doses to really optimize the performance for the plant specific needs. And then screening equipment. So this is a sludge screen in action. So this is offloading from a truck going into a digester. So we can feed sludge directly through the machine and into a downstream tank or digester, and you can actually see what is being removed from entering the downstream process. So in this instance, this material is being removed from going into a digester downstream. So wrapping up, I just want to point to a couple of additional resources that I've found very helpful in my own research and my time on the Residuals and Biosolids Committee. The Residuals and Biosolids Conference this year will be in Charlotte, North Carolina. Huber is based right here in Charlotte, so we will be in attendance. It's the Dewatering Optimization Workshop is a great workshop that the Solid Separation Subcommittee and Residuals and Biosolids Committee puts on together. Be sure to sign up for that if you plan on attending the Residuals and Biosolids Conference. There's a lot of people that I've learned a great deal from that will be presenting at that conference. So a great chance to hear from researchers, engineers, operators, and manufacturers in the sector. Again, we will be in attendance both at the pre-conference workshops and at the conference itself for consultation. If you have any questions specifically on screening, dewatering, thickening, drying, we will be there. Then the Water Environment Federation, there are operator fact sheets and several upcoming publications and videos on their website. So I would just say stay tuned for that. There's a lot of great stuff out there that could serve as a really great resource. And with that is it. I just want to say thank you and open the floor for any questions.
Christian, can you hear me? Christian. You got Mark?
If anyone's talking on the GPSD side, I think you're on mute and I cannot hear. So just wanted to let you know.
Okay, can you hear us now?
I can.
Okay.
Yes.
Does anybody have any questions?
I think we're all good, Christian. Thank you very much. We all greatly appreciate it. Hunter had to step out.
Yeah, absolutely. Happy to, if anything comes up, any questions or comments, feel free to shoot them my way. I'd be happy to answer those at a later time if need be.
Okay, thank you very much, Christian.
All right. Yep, thank you. All right, bye now.
Bye.